Okay. Greetings. Welcome to the third class of time series methods for astronomy, offered by 3 universities. I've never taught in 3 universities before in the same time. My name is Eric Feigelson. It's our third class. We don't have to go through that. Let me spend a few minutes, though, talking about the class. I have updated the syllabus, and I handed it out to people in the room. It is, oh, I didn't put it on the website. I'll put it on the website afterwards. Okay. What I've done for myself is I took out a lecture sort of towards the end on Fourier analysis, partly because I don't have that much to say, and partly because it really is more introductory, you know, sort of fundamentals, and should be in the beginning and less at the end. It's not research oriented. So that left a spot called TBD, to be determined, and we'll see what happens. Maybe I'll do it, maybe you'll do it, maybe some visitor will do it, and we'll just see what happens in March 29th. So I changed the title here from time domain to time and frequency domain analysis. So I will do all of that today in one big 2-hour lecture, sort of. Okay. The other thing is that we really do have confirmed visitor speakers. Their titles and their dates are confirmed by them. They know you're here. They want to do this. You are fortunate to get such talent, in my opinion. I will not physically be here. I think I may be here for the 8th physically, but I'm not going to be here for these weeks here because I have other responsibilities that are not at SAMC. So I'm at SAMC here for 5 weeks roughly, and here for roughly 7 weeks, and I'm gone for that. So what I'm going to do is I'm going to watch the video that we're making and from Pennsylvania and see how it went, see what I learned from it. There's no final exam in this class, ladies and gentlemen. So it's not as though you have to learn everything. It's really a question of opportunities than it is responsibilities. Your responsibilities are homeworks, of which the second one I'll talk about in just a second, and a project. And the project is more creative. Okay. There'll be at least 3 homeworks. This is the second. I haven't decided if there's going to be a 4th one. TBD. Okay. I put okay, so let's get to the homeworks, which the homework number 2 rather, that I just handed out in hard copy. And here it is on the screen. So the first one, as you know, was just really elementary issues in R. So now some of you know R well, but others less well, and it was laying foundations on methodology. We will do R in class next week, where I will go through a tutorial that is both meant to sort of educate in R, talk about R and CRAN and just how things are done and what it's like, and also it happens to be a question of smoothing. It's a useful technique for time series in general, and particularly for irregularly spaced time series that you want to smooth through the irregular spaced observations and make something that you don't really know, but you want to estimate a smooth temporal behavior. So that's next week. The homework is quite substantial in the sense it's not just one thing and maybe even 2 things. It's like 10 things, okay? And so I don't expect you to go through the homework in like an hour and whip through it and grasp it. If you can cut and paste my stuff and do it in an hour. But I don't recommend it. Because every little bit is going to be using some part of R or CRAN and a method that you may have heard a little bit about from me, for instance, today, but not much. So that means you really should study. You take a little bit, and you said, oh, well, look, it took the time series that did that. Oh, let's look at the help files. See what the help files, the explanations, not so much the mechanics of running it, but the explanations. And then look at the, see what the references are, and then maybe go to Wikipedia. That's sort of an easy way to learn intermediate level statistics if you don't know the methods to go to Wikipedia and say, oh, well, what's going on with a wavelet transform? What's going on with a Fourier transform? What's going on with this or that? And of course, in principle, you would study even deeper than Wikipedia, but I'd like to leave that for the project. But the nice thing about my homework is that it's going to expose you to a lot of different time series and ways of looking at things. And so you might look at it and you say, well, I don't like that. I don't like that. I sort of like this. Good. That's your homework. Your homework, look at the bottom of the third page. Okay, that's where I actually say, what's your homework? Okay, so first cut and paste through the whole thing and learn it. Spend some time slowly and going through what I'm doing. Okay, it's from my textbook. And then you choose. You choose some portions. Maybe 2 or 3 portions, or if you really want to deeply get into wavelets, then just do 1 portion. Okay, choose some portion where you start where I am. You don't bring in new data sets. Use my data sets, and so that's easy. You don't have first homework and project. You need to find data sets. This one you don't. Okay, but develop the analysis further. Start where I am and go further. Maybe, for instance, it's a very complex function that I just used once. Okay, it has many, many sophisticated options. Well, maybe you want to spend some time and learn linear modeling or ARMA or spec-p-gram that makes Fourier periodograms, or something, or RobPer that does all sorts of astronomical periodograms that are not standard in time series analysis. Choose something you like and develop it, both using the same functions that I give, and if it's from a CRAN package, often there'll be related functions around it, or other CRAN packages that are sort of rivals to it that do similar things. So if you do wavelets, there's probably 10 wavelet toolboxes around. It's be fascinating to see how they each do something, one thing on one data set, but how different codes deal with it, and different approaches. And in the text, as you know, I want a LaTeX document with figures and R scripts. Well, if it's a Jupyter notebook, the R scripts are literally inside of it. If not, the R scripts are just submitted separately. But the figures are inside, and then you talk about it. You say, well, I ran this one, and it gave me the figure 3 over there, and well, look, it really did a lousy job. So I tried harder, and I found something else in figure 4 much better. I really like it better. Talk to me. Okay. Now, I'm not interested in the stars. I'm not interested in X-ray accretion. I'm not interested in astronomy or astrophysics. I'm interested in you talking about methodology to me. Okay. Talk about what the methods did for this time series. What did you learn? What could you learn if you were an astronomer from this? Okay. Sound okay for the second homework? The reason there's 2 staples is that after I gave you the doc file that describes in some text what's there. I decided, hey, well, I might as well give you the R script as well on paper. Look, I'm old. I actually use paper, I'm sorry to give you paper. But all of this is available on the website. The website is still on here, www.astro.psu.edu/user/EDF and TMSA SAMSIN 2017. And that is in the syllabus as well. Everything is both there electronically, and for those of you who come to the room, I give it to you on paper as well. Okay, what do you think? Any comments about the improved syllabus? The course is more or less solidifying. And what do you think about homework 2? You feel okay? Okay. Did the sign-up sheet go around? Okay, it's complete then. Thank you very much. If someone walks in, David, have them sign. Okay, so that's it for the course. Any other comments or questions or criticisms about the course as a thing? Okay. Now let's get to a lecture. So this is one of those lectures that nobody should give because I'm summarizing essentially an entire textbook of time series analysis in 2 hours. And anyone who knows anything about any field knows that's impossible and shouldn't be done. So what I'm doing instead is, not instead, but the way I do it is I tell you the things I want to tell you as though you're astronomers. In other words, the things that I think that are most interesting or relevant to astronomers. And you remember I gave a few slides at the very beginning, the first lecture, on the characteristics, the peculiar characteristics of astronomical data sets. How there's all sorts of things. There's periodic and aperiodic and stochastic and explosive types of behaviors. We often have gaps and they're not evenly spaced, although the examples I'm giving you in the R homework 2 are either one of the GX one is completely evenly spaced. And the other one is evenly spaced with some missing data, but not too much missing data. Just almost evenly spaced. Okay, but and this lecture is mostly about evenly spaced methods. Okay, so let's get to this as a lecture. Full screen mode. Time series analysis in 2 hours from beginning to end. So I'm going to do concepts. I already did this one. Concepts, time domain methods, frequency domain methods, and then something about non-stationarity, and then references. Okay, so of course, please remember, astronomers don't use the word time series, they use the word light curves. I don't know where that comes from. I'll guess to say 19th century? I don't really know. Okay, it's really old. But I'll use time series. Okay, so now we have a time series. We have, I'll think mostly in terms of univariate. A single variable is measured in some phenomenon that might be changing. In principle, the time series could be absolutely constant with just Gaussian white noise. In fact, that's the default, okay? That there's no trends, there's no autocorrelations, there's no periodicities, but there's always some noise, okay? Otherwise, it's just a constant number, okay? So there's actually that simplest time series there's actually theorems associated with it. So for instance, the autocorrelation function we're going to see actually has theoretical confidence intervals, 95% intervals, for that case of constant Gaussian white noise. But in most cases, of course, if everything was like that, there wouldn't be any interest. You just take the average of them, you get a mean, and you look a little longer, you get a more accurate mean, and that's the end of it. But we're not interested in such simple time series. So with all the different things that astronomers see, what are some of the sort of conceptual characteristics in technical language, okay, or semi-technical language? Okay, one of them is called stationarity. Stationarity, whether or not it's a deterministic phenomenon like a rotating ball that has a red spot on it and the spot goes around and it sees, or an orbit it's deterministic or stochastic, some blobs of gas swirling around and doing things. Stationarity means that it's statistically unchanged, whatever the behavior is, with shifts in time. So basically, if you have a time series, a single measurement of some quantity as a function of time, that the behavior at the beginning and the middle and the end has the same characteristics. The same period if it's periodic, the same stochastic characteristics if it's stochastic, the same mean level, the same variance, the same everything. That's called stationarity. Okay. So obviously, most things are not stationary, or at least many things are not. Okay. So, but excuse me, even if you have a stationary time series, it still is interesting. Because you still want to find the period if it's periodic, and the shape of the periodic behavior. You still want to find the stochastic autocorrelation behavior if it's stochastic, even if it's stationary. So it's not as though there's nothing to do. Okay? It's not the same as Gaussian white noise with constant mean. Okay. So types of non-stationarity include trends. Trends means the mean value is changing. So the mean value of the velocity of a binary star in elliptical orbit looks like this. Here's one star, here's the other one, the planet or the other star. That's a non-stationarity. That's a trend. Okay, well that's a periodicity. Okay, but a trend, it's going those are trends. Could go up, could go down, could be something deterministic, something stochastic, it could be weird, it could be explosive. Trends, secular changes in the mean value. Another type is heteroscedasticity. Instead of the first moment changing, that's the mean, the second moment is changing, that's the Gaussian noise scatter. So it could be viewed as heteroscedasticity is also sometimes called volatility. There might be sometimes when it goes and sometimes it goes with whatever mean, whether it's a constant mean or non-constant. The variance is changing. The kind of heteroscedasticity that astronomers often see is heteroscedasticity produced by the measurement process. And we, unlike all the social scientists and most biological scientists and most engineering scientists, we actually measure our measurement process incredibly well. So we actually get these measurement errors for each and every time that we measure something. Not all the time, but very often. And so we have our own sort of weird form of heteroscedasticity, where the heteroscedasticity of the measurement part of the behavior of the time series is known, has known variances. So we actually write down the brightness is 14.2 plus or minus 0.1. Next day, night, we look 14.2 plus or minus 3. It's a really bad night for observing. Okay. Next night, 17.5 plus or minus 0.4. Has a different mean and a different variance. And we know those variances. Sometimes the only source of variance is the measurement process. Sometimes that's not true. Sometimes the object itself has a stochastic variation as well. Sometimes the object's stochastic variation is so much bigger than the measurement error that they might as well consider the measurement error to be 0. It's just effectively it's a precise measurement compared to what the craziness of the object. All three types of heteroscedasticity are seen in astronomy. Intrinsic to the object, intrinsic to the measurement, intrinsic to the object only, intrinsic to the measurement process only, and both. Welcome to astronomy. Okay. So, but be aware, the astronomer doesn't really want to hear this because they've been taught to always pay attention to their measurement errors. Okay, and they haven't always been taught to pay attention to the scatter intrinsic to the object. Be aware that sometimes it's just wise to just throw the measurement error away. Sometimes the methods we have available to us from time series analysis simply don't allow heteroscedastic weighting of the points. Sometimes they do, and sometimes they don't. A linear modeling or regression type problem often does allow weighting. A Fourier transform does not. A wavelet transform does not. So what do? Ignore it. It's just scatter. Happens the interpretation of the scatter is different. In one case, the quasar or the star is varying. In the other case, your telescope varied. But in terms of the data themselves, it doesn't matter. It's your scientific interpretation that matters, that cares about it. So be aware, astronomers don't like to throw away the data set, the measurement error. But you can, and sometimes you must. Okay. Alternatively, you might try to make the data as homoscedastic as you can. And a good example is if you have some minority of points with enormous measurement errors, just throw them away. I mean, you barely know anything from them. There's hardly any information in them. Throw them away and call the rest homoscedastic. And leave it at that. Okay, another type is change points. And one can consider it the trends in heteroscedastic sometimes can be viewed as change points. But there's actually a whole field called change point analysis. And change point analysis is saying that the object is sort of cruising along and varying its favorite way until a special time, and then it goes crazy. It just changes phase. It goes at a certain time. The left and the right side are really different. But they're consistent over there, but it changed. And one of the parameters of the model is t0, is the time it changed. The simplest one is that it just changed level. But constant. So that would be constant with change point. There could be several change points. Okay? So change point analysis often has the time of the change as part of it. Interestingly, you can have autoregressive behaviors and have the same mean, but different autoregressive behavior. Same mean, didn't change values, it changed its behavior. Maybe periodic with one period, and at this point, same mean, but different period. Frankly, I don't know how that would happen in astronomy, but in principle. Okay. So change points are really interesting. And I happen to have checked recently. There's 3 monographs on change point analysis, specifically techniques for change point analysis. No astronomer's ever read them. I mean, no astronomy article has ever referred to them. So, well, there's something we don't know. Okay. So that's interesting. Oh, and I showed my favorite example. Remember GRS 1915 that had at least 20 different states, this crazy accreting black hole? And those are all change points. I mean, it has weird behaviors, but it also changes behaviors, and those are the change points. Okay, all of that's the issue of non-stationarity. Okay, then there's periodicity. Periodicity is the measured levels repeat themselves deterministically with a fixed period. You can't mess with your phases, it's deterministic. It actually is 3.199242 hours. That's the period. Now, what doesn't have to be true is that it's always a sine wave shape. It could be periodic dips from eclipses, periodic explosions from, I don't know what would be periodic, but it could be periodic behaviors that are not necessarily sinusoidal. But periodic implies strictly periodic. Astronomers have this word called quasi-periodic. It's in one of your homework sets, QPOs, quasi-periodic oscillations. And the weird thing is that they always view it as a messed up periodicity. And often that is unwise because they end up always using Fourier analysis, because Fourier analysis is really good for strict periodicities. And they don't realize that often autoregressive models are very often quasi-periodic on short timescales. If you have an infinite duration time series, autoregressive are not periodic. But you take a piece of it, there's very often a quasi-periodicity in there. And it looks periodic. And I can't tell you how many times astronomers report, hey, I found some quasar or some star, it's quasi-periodic, or I think it's even strictly periodic. And then they collect more data. And they say, oh, the period changed. Oh, the period changed again. Well, it's not strict, and it changes phase. And I can't tell you how many times they just get confused because they only think in terms of strict periodicities with Fourier analysis. And I say, hey, why don't you just run an AR model and see if it works? I'm not sure it will work, but if it works, then you know that at least there's a existence proof that there's a completely aperiodic phenomenon that models that particular time series perfectly well. Okay? So whenever you have things that look periodic, but don't seem to be exactly periodic under the Fourier transform or something like it is, it does not have an absolutely narrow peak, as narrow as you can get from your data set, then I recommend you also run autoregressive modeling to see if it works. It could very well be that you can model it both as a periodic behavior and as an aperiodic autoregressive behavior, and you really don't know. And that's right. From that data set, that's not enough to tell the difference. Your science analysis has to have 2 parts to it, and you have to conclude that both of them worked. I don't really know. Okay? So periodicity is actually a problem for astronomers because they're so used to strictly periodic behavior from the 18th century celestial mechanics, where all the orbits in the solar system are absolutely perfectly periodic, with one exception, by the way. Okay, they're so used to things being strictly periodic that they thought everything should be analyzed this way. But if you do analyze it because you really think it's periodic or you want to check it, it has, and this is where I'd love if any of you happen to know, you statisticians, what's the difference between spectral analysis, harmonic analysis, and Fourier analysis? I haven't been able to figure that out. As far as I can see, those three phrases, those three sort of domains overlap tremendously. Some of the books are called harmonic analysis, some are called spectral analysis, some of the books are called Fourier analysis. As far as I can see, they cover more or less the same thing. Okay. And their heritage mathematically is Jules Fourier. 1807 or something was the major book or something. So it's really old. It's 200 years old mathematically. And in terms of celestial mechanics, it's 250 years old in terms of astronomy. So periodic behaviors were very, very heavily studied in astronomy in the 19th century and the 20th century. It's really only the 21st that we get to all the messiness of non-stationarity and autoregression and quasi-periodic periodicities and things like that. Okay. Now I've mentioned autocorrelation, but let's take a look, okay? So autocorrelation means that the measured levels at time 0 depends on the values from previous time. Time -1 or -2 or -10 or something like this. That should be a minus sign. It could be a plus sign, but it's usually almost always a minus sign. I apologize. I just noticed that. This old slide has an error. Okay. The autocorrelation can be deterministic. That, to know the value right now, you just have to look at 3 previous values and do some arithmetic, maybe even linear relationships, okay? And that absolutely precisely determines what the value is now. That would be a deterministic autocorrelated process. Okay. More commonly and more generally, we have a stochastic component. We have a dependency on previous values, but we also have a random Gaussian noise. We assume it's Gaussian, a random introduction to some randomness. And that means that affects the future, because the future is, that becomes the second and the third and the fourth oldest one to the future points. And each one of them has a dependency, a deterministic dependency on the previous ones, and its own, and something called an innovation term, which is really a Gaussian, assumed to be a Gaussian noise. Okay. Now we're going to talk only about evenly spaced-time series at this point. So the autocorrelation function is the fraction of the total variance that is due to correlations at lag k. So how much of the variance is associated with lags of just 1 from the previous data point? How many with 2? How many with 10? How many with 100? That's the autocorrelation function. There it is. ACF, autocorrelation, or rho, as a function of lag k, there's a variance. It's the value minus the mean, the value, of the kth previous one minus the mean, multiply them together, divide by the total variance of the system. So it's a fraction. Can never exceed 1. In fact, if k is 0, this is 1. So it always starts at 1.000. And then it goes down. It could be 20% or 10% or 0.003%. It could be anything. It can be measured it's non-parametric. There's no parameters involved. It's a wonderful non-parametric measure of any time series, autocorrelation function. You should always do it because it's just so informative. Okay, and it's one little line of R. It's cute. Okay, so if the autocorrelation function has a significant signal, and I'll get to the word significant in just a minute, at small k, at small lags, then it's called a short memory process, or short-term memory process, or something like that. If the signal extends to large k, it's called a long memory process. I happen to know there are 2 books in statistics on long memory processes. 3. 2 by statisticians and 1 by an econometrician. Okay. All 3 of those books are super hard. I mean, I can get to page 20 and I just die. Okay. And the answer is that long memory processes are often really nasty mathematically. For instance, it's not uncommon that as you get more data, instead of you learning things like the means and the variances improve with the central limit theorem, square root of n improvement, they diverge. Infinite data, infinite variance. Infinite variance! Oh, it's horrible. So the mathematics is sitting there trying to divide by 0, it just crashes and stuff. So not all the time, but some long memory processes are really nasty mathematically. It's very difficult. It's very difficult. And sure enough, I show you half a dozen estimates of the Hertz parameter or the alpha parameter that you'll see in the homework. There's the alpha. And the estimates are inconsistent with each other because of these mathematical difficulties. There's no consensus on how to characterize these processes in a way that everyone agrees is the best way with really good behaviors and asymptotic, behaviors. So this is this thing called red noise. This is it's a parameterization of long memory processes. You can have a long memory process that's not 1 over f to the alpha. But if it happens to be 1 over f to the alpha, it means that if you take the log of the Fourier spectrum and the log of the frequency, it's a straight line on that log-log plot. And that also was known as a power law in frequency. The power is a power law in frequency. It ends up that 1 over f noise and red noise systems are often seen in astronomy. They're often seen in other physical systems, like electronics of your detector may drift with 1 over f noise. The sky may sort of fluctuate in 1 over f noise. And your star or your quasar or your accretion system may have 1 over f noise. So it ends up that I could say, hey, well, there's 3 books on this difficult problem, but fortunately we don't have to think about it. Unfortunately, I have to say, there's 3 books on this mathematically difficult process, and astronomers often have to think about it. To my knowledge, no astronomer has ever read any of those 3 books. There's a great deal of ignorance of everything except for Fourier analysis in the astronomical community. It's a real problem of education. They don't even know the simplest elementary book, Chris Chatfield, 6th edition, Introduction to Time Series Analysis. Undergraduate level, very informative little book. Boy, Chatfield writes a cute little book. We should all have that book on our shelves. It's so cute. I mean, so compact and informative. Astronomers don't know it. It's astonishing what they don't know. As a community. I'm not talking about Jeff Scargill. I'm talking about as a community. Okay. A stochastic time series with insignificant autocorrelation at all k's is called white noise. And it doesn't have to be Gaussian. It could be Cauchy. It could be uniform white noise. But if the distribution of the values of the white noise with 0 mean is Gaussian, then it's called Gaussian white noise. And that is the usual assumption for epsilon, the innovation terms on virtually everything is Gaussian white noise. Why? Because, well, I don't know, you're statisticians. You've assumed Gaussian errors on most things for 2 centuries. And it's good and nice mathematically, and it often works. Not all the time, but often. Okay, other important concepts, sort of like vocabulary lesson in time series analysis. Each of these, there's some monographs out there. These are not small. Okay. One is nonlinearity. You're going to see, for instance, with the autoregressive modeling, we're going to only deal with linear models. Well, why linear? Okay, trends might be piecewise linear or piecewise parabolic, which is a very simple polynomial. Okay, but what about really, really nonlinear systems? So that the dependencies, whatever they are on the past values or dependencies on whatever, are tremendously nonlinear. In fact, all of these Fourier behaviors are nonlinear. But if it's stochastically nonlinear, they're sometimes called chaotic. So chaos. So chaos was really popular when I was younger, like 20 years ago. Everything was chaotic. And I don't mean chaotic in the sense of just being hard to understand. I'm talking about strict, formally chaotic with Lyapunov exponents and period doubling and other characteristics of nonlinear dynamical systems. In physics these things occur, and sometimes in chemistry they occur. Chaos. I think they occur sometimes in certain biological systems, like ecological systems. So Jeff Scargill is the leading time series analyst for 30 years in astronomy. Jeff Scargill once wrote an article that nobody reads on chaos in astronomy, and he couldn't find any. There's only one system he found that's formally chaotic. Okay, I'll try to get it right. It's the tiny moon called Hyperion orbiting Saturn. Its orbit is not an ellipse. It's a chaotic combination of ellipses because it's being pulled on in a nonlinear fashion by too many other moons, and it's too tiny, and it's chaotic. That's it.
So how's that orbit? It's not elliptic, I understand that.
Well, at any moment it sort of looks elliptical, but if you go back later, it's a different ellipse.
Okay.
So it's not exactly an ellipse. Okay. And that's because it's a several body system.
It's a randomization on the space.
Yeah, and strictly speaking, all in the solar system, everything is pulling on everything. So none of them are really absolutely ellipses, but they're so accurately ellipses that even in the time scale of the whole solar system, their orbits are not chaotic. Okay. But certain asteroids and certain moons can have chaotic, and that's about it. So chaos is actually not an important topic in astronomical time series. Okay, there's multivariate time series. And in economics, they're very interested in these things, and I'll tell you why. Okay? I'll give you two time series. Ready? Here's time. Here's month of the year, or years, or days, or something. Here's the price of wheat. And then here's the price of bread. So the price of bread is made from wheat. But it takes a while to farm the wheat and bake the bread and sell it in the store. Okay. And who knows, the businessman makes some pricing decisions. Okay. So generally speaking, you have these multivariate data sets with lags. And we happen to understand bread and wheat probably pretty well, but they don't understand, let me see if I can get it. Unemployment rates and, I don't know, give me some other macroeconomical thing. Anyways, macroeconomics is full of these things, okay? Many variables, all jumping around, but they're related to each other often with lags, okay? And they're often autoregressive. They don't jump crazy. Today's is usually related to yesterday. So it's very common to have that kind of behavior in economics. In astronomy, it's not so weird, okay? In astronomy, we go and we observe, think of Ashish Mahabal's CRTS, think of the new LSST instrument. We will observe the sky. Actually, CRTS may only have one band, but Sloan had 5 bands, Sloan Stripe 82. I'm speaking astronomy to those of you who don't get me, okay? We have these data sets. These data sets cost tens of millions of dollars to $1 billion. The LSST is $1 billion. Hasn't been built yet, the telescope. It's being built now. So we have these, and we tend to get about 5 or 6 time series that might be observed at exactly the same moments or not. Slightly different moments, which is a big pain for time series analysis. Okay? So we actually do encounter multivariate, but most of astronomers deal with univariate data sets. Sometimes bivariate, but usually they sort of stay to univariate. But in principle, low-dimensional multivariate is going to be common. Time frequency analysis is sort of a variant of frequency analysis, a Fourier analysis. It means you do Fourier analysis, but the period is strict at a given time, but it's strictly deterministically changing with time. So it is non-stationary periodic behaviors, and you therefore do a 3-dimensional thing. You do the Fourier analysis as a function of time, and in strips in time you do the Fourier analysis. It's for non-stationary periodic behaviors. Actually, it shows up in some stars. I forgot their names. Multiply periodic stars that sort of change their periods. some stars are pulsing. They're made out of gas, and the gas is not totally stable, and they pulse. But they don't pulse sort of in a simple fashion. Sometimes the pulsations sort of change and pulses differently a week later or a year later or a decade later. And these things are known, and we astronomers sometimes use time frequency analysis. Now, wavelet analysis has proved to be really quite good for astronomers. Remember I said there are explosive things. Something happens, and all of a sudden it just goes, and that's the end. Either it never happens again, or sometimes it's repeated at uneven times. But there's really phenomena that happen just at July 3rd in 2014. Something happened. Okay, so a wavelet is passing a filter, usually not a Gaussian, but some sort of a filter that is low and goes up and goes down again. And it passes it through the data set, and when something happens on July 14th, 2014, it captures it. It gets a high signal right there. And you capture the amplitude of it. And what wavelets do, they have different scales. You first pass through sort of skinny ones that look for rapid events, and then you pass through fat ones, and you look for slow events. And so what you get is then amplitudes as a function of scale and a function of time during the data set, during the time series. It's really quite powerful. By the way, it can be applied to periodic phenomena. It will capture the periodicity. It's sort of not a very compact way of collecting the periodic information. Fourier analysis is better for that, or some other periodogram, some sort of strength as a function of frequency that's stationary. But wavelets are really good for non-stationarity. It's good for trends. It's good for explosions. Good for just things are different at different times, non-stationarity. So wavelets are actually moderately popular in astronomy. Similarly, they've become popular in engineering and other fields. They're quite important. R is full of wavelet analyses. and there's a book on wavelet analysis in R. And there's a whole slew of books, mostly from the engineering world, on wavelet analysis, the mathematics of it. Jogesh Babu, my colleague, professor of, a mathematical statistician, he often sort of looks down at some of the more advanced methods as sort of, they're just ad hoc methods. He does not look down on wavelets. He says the mathematics by, her name is Debussy. She wrote it down 30 years ago. She's a mathematician. She wrote down the foundations of wavelets. He says it's really beautiful math. Has a strong foundation, like Fourier analysis, a strong foundation. So Jogesh likes it mathematically. But it's really nice that he likes it and we like it. It's useful. Okay, here's one I'm not going to describe. State space modeling. It's a variant of things. You're going to see that often models, particularly autoregressive models, but it could be deterministic models, are solved the way we do other regressions. We take the time series, we have a measurement as a function of time, and we do a regression, and we have to optimize something, least squares, minimize the sum of square residuals, or maximize the likelihood. And MLE, maximum likelihood estimation, is widely recognized to be a very powerful approach to parametric modeling. State space modeling is just, as far as I can see, jargon for a particular formulation of MLE that was made in the as far as I can figure out, 1950s and 60s before they had computers. And this was their problem. They would have a time-varying situation. They had a parametric model for it. They would want to get the coefficients, and they would do it. They would take it and they would do it by hand because they didn't have computers. And then there would be more data. And they'd have to do it again. And again, and the data set grows and grows, so it gets bigger and bigger computation. So state space modeling was a way of taking the first hunk of data, finding the state of the system, in other words, the coefficients of the regression of the model, and then updating it in a computationally easy fashion. It was not burdensome, because they didn't have computers. So they would update the state and change it a little bit as time went on. They got more data. And it was just easy. And that's why state space modeling. It's not really a new principle. It's just a convenient way of doing MLEs for time series. The updating process is often called the Kalman filter, 1950s. Kalman was, I think, an engineer. As far as I understand, excuse me, I'm really ignorant. I don't know why it's called a filter. It's really just a nice algorithm for updating parameters, okay, of a regression model. It doesn't have to do with time series necessarily. It's a trick. Like the EM algorithm is a trick for maximizing likelihoods. It's a trick. So it just happens to be a trick that's very well adapted to time series. And as far as I understand, Kalman filters and state space models are still used today, mostly by engineers and maybe somewhat by econometricians. I've never known, I know one talented astrostatistician who used it, Brandon Kelly, in one of his papers, did a state space model. But it's really just a formulation of regression, of a parametric model regression. Okay, and then there's a concept that's completely missing in all the books I can find in the Penn State Library. Almost all of them do not even have a chapter on what astronomers have all the time, which is the unevenly spaced data set. So what they would probably say is, well, if it's unevenly spaced, well, just interpolate it onto evenly spaced and pretend it's evenly spaced. And we're going to do that next week. We call it smoothing, interpolation, or imputation. Those are three related words. But often our data is so unevenly spaced, it's basically hopeless to fill in the gaps. I mean, you can try, but it's really hopeless. So we need methods that deal with intrinsically unevenly spaced data. Guess what? Astronomers are smart. We're not very knowledgeable in advanced statistics, but we're smart. So starting in the 1970s, we developed a bunch of methods for unevenly spaced data, particularly for periodicity searches, but also things like autocorrelation functions and things like that. So this subfield is of which there's 0 books, and there's not even a major review article that I know of that collects it all. So my lecture here does as good a job as I've ever seen, and it's not a very good job in my opinion. Okay, let me speed up a little bit. Let's start a topic. Time domain methods. Time domain means we're going to look at the time series and analyze the time series. Okay? We're going to do non-parametric time domain methods. No parameters, no regression. We don't have a model. Okay, so the most important tool is the sample autocorrelation function. As I said, it's the correlation between, I got the minus right in this slide, of an evenly spaced time series. If it's 0 mean and normal Gaussian errors, then there's asymptotic theory that the variance of the ACF is just this simple computation. Where n's the number of points, k is the lag. This means that you can make probability statements. So if you have a value of 14% autocorrelation for k of 11 for this time series with 2,714 points, n, you plug in n, you plug in k, you get the variance, take the square root. You now know the standard deviation for the null hypothesis of 0 mean Gaussian errors. And if your number's too high, it's significant. You can do probabilities. Hooray! Standard statistics works. Almost nowhere else in time series analysis is it so clear, so simple. Okay? So every time you do an ACF, they put these dashed lines that represent the 95% confidence, or 99%, or whatever you want. And astronomers tend not to do that because they tend not to know this basic fact. But R knows it. Whenever R does an autocorrelation function, it draws in the dashed lines, the confidence intervals. It's very useful. It's really useful. It's tremendous. Okay. Now here's one that's not as, it's completely unknown to astronomers, and I can't find much about it among statisticians. It's called the partial autocorrelation function. And it was developed by some econometricians 50 years ago or something. And what it is that the autocorrelation function itself has autocorrelation. So the autocorrelation of the dependency of the k of the fourth one involves the autocorrelation of the third and the second and the first lag as well. So it's very easy to write down the autocorrelation function, but it's actually autocorrelated. So if you want to decorrelate it and say, well, how much of the dependence of this one, of the current value is precisely due to the fourth one, please ignore the ones in between, you need to do an iterative algorithm. I think it was Durbin who did it. Durbin's a famous, important econometrician from the previous century. Yeah, Durbin. So there's the algorithm. There's no formula. I can't write it down, but it works. Okay? And I think the PACF is often more informative to the astronomer than the ACF. It also, I think, has confidence intervals, analytic confidence intervals, for the null hypothesis of zero mean Gaussian noise. Okay. This is what I'm going to cover next week, so I'm not going to talk about it now. But density estimation is the jargon in statistics for what astronomers would call data smoothing. It means making a smooth continuous distribution out of irregularly spaced individual measurements. Okay, so I'm going to skip that. Okay, now we're going to get to what is in your homework. The first data set in your homework is this data set. So this is a star. It's actually two stars orbiting each other in the galaxy. It's actually fairly close to the galactic center, where the stars are very crowded. And one of the stars was massive and exploded in a supernova. We don't know when. Probably not billions of years ago, probably tens or hundreds of millions of years ago. But the other star wasn't blown away. Sometimes they are, but it was still orbiting. So now you have a normal star, the one that didn't go supernova, orbiting what's left. In this case, it's a neutron star that's left. If you don't know, after the explosions, you get white dwarfs, neutron stars, or black holes. Okay, it's great stuff. So now this one starts evolving, becomes a giant, and the gas starts flowing on and spiraling onto the black hole or the neutron star. And you get an accretion disk falling onto the compact star, and it gets incredibly hot in the inner part of the accretion disk, millions, tens of millions, hundreds of millions of degrees Kelvin, which means everything is ionized and the thing is just going berserk. And it emits vast amounts of X-rays. This kind of system may emit 10 to 30, 100,000 times more luminosity than our sun. You understand, the stars are not much more massive than our sun, so it's just, so it's 1,000,000 times more luminous, but instead of emitting yellow light like our sun does, it's emitting it in X-rays and gamma rays. Okay? And it's emitting it not from the star, but from the, actually it splashes onto the star, it emits there too. It emits a lot of places, very complicated. These time series often show red noise and QPOs, quasi-periodic oscillations, probably from inhomogeneities in the disk. Even though there's been about 1,000 papers by astronomers, X-ray astronomers on these things, they still don't fully understand the behavior, the physical cause of the behavior. So the data set I'm giving you is 65,500, tens of thousands of count rates from a satellite that was launched by the Japanese Space Agency 30 years ago. So I'm not going to discuss the R because the R is given in your homework. It's also extremely easy, R. So there's the first 10% of the data set. So the typical value every time it's being measured is around 70. And you can see that, let me see, 70, what's the square root of 70? About 8. So you expect that, let's say, 70 plus or minus 10. So you expect most of them between 60 and 80. Okay, that looks about right. Okay, it looks about right. It looks like it could be Gaussian white noise. I don't see any trends. This is only 10% of the data. But this way you can see every point. Okay, so one thing you might want to do is smooth it. This is a kernel smoother. I won't go into it now. Here's a bunch of smoothers. I won't go into it now. But take a look. I'm not so sure that it's always Gaussian white noise. It sort of has looks like a mountain range here. But this one looks very smooth, that one looks smooth, that one looks pretty smooth, but these look like mountain ranges. It's not obvious. Certain smoothers look sort of noisier than others. It's not clear. So it ends up that if you want to know, is that Gaussian white noise, it's not that helpful to look at the time series and even to smooth it. I mean, you should do it, but it doesn't always tell you what you want. So what does tell you something is the autocorrelation function here, and the partial autocorrelation function here. All of a sudden, except for the zeroth lag, that's always 1.0, all of a sudden you immediately see that at one lag it's 23% autocorrelated. And that it's autocorrelated for several lags up to about 10. And then it seems to even have this blue, 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 blue. And it doesn't die away till you get out to like 30 or something in the autocorrelation function. The partial autocorrelation function actually shows this positive, negative, this periodicity even more clearly. And there it is. Look at the dashed lines, ladies and gentlemen. Look at the dashed lines. That's 95% confidence intervals. It is significant, very significant. So the autocorrelation function instantly told you what looking at the data by eye didn't tell you. Even smoothing the data and you weren't quite sure, you instantly found out it's an autoregressive process. So what do you do when you have an autoregressive process? Well, you don't have to, but you might want to do parametric autoregressive modeling. That was non-parametric. Now, if we see something significant, maybe we can try a parametric model to see if it reduces the variance, brings it down essentially to white noise. So this, ladies and gentlemen, is what most time series textbooks all talk about, and what most astronomers don't know because they just don't know it. So it's very common in many, many things for all sorts of autocorrelated time series is, and they're easily fit, they're parametric, they could be like polynomials, you've just run maximum likelihood on it, okay? And they're called ARMA models, A-R-M-A, and here's the math. Oh, the disadvantage is that most people don't understand what the coefficients mean. And so it tells you the dependencies of all the previous values of the time series. That's the AR component. X of t is related to x of t minus 1, t minus 2. Linear, these are just, these phi's are just numbers. Could be 1.39. It could be minus 0.42. These are just numbers. They're just coefficients of a linear regression. MA is a little weirder. That the value today is there's thetas as the coefficients is linearly related to the recently passed values of the noise. There it is. And usually it's called epsilon. I don't know why I used W here. Okay, but that's usually considered to be a normal random deviate of zero mean and homoscedastic a single variance, but it has a value at every time. It's a random Gaussian number. It's a value, and you got to remember those values and that there's a dependency in the moving average of the current value to the previous ones. The simplest one, MA1, is well known to physicists. In fact, we teach it in elementary physics. MA1 is the random walk. The drunkard's walk. Same step size, but random direction. This is the time series. My position or distance is the time series. I go, by the way, as the square root of time away from the origin. I can zigzag back, be on the other side for a while, and stuff like this is called a random walk. So these are generalized random walks to the physicist, for the astronomer in the rooms. Okay. So we sort of can imagine you could do it. You might say, well, why bother doing this? All I could say is that it seems to work. It seems to be highly applicable to many, many autoregressive systems. Many, many time series systems that have some sort of autoregressive behavior on this graph are well modeled with this kind of model. Okay? So It's recursive with the memory of past values. It's linear, but it's linear not in the value of t. Usually, like we have x is equal to a linear function of time, like parabolic or exponential or something like this. No, it's a function of the past values. So it is weird. It's linear. It's a linear deterministic system, but it's deterministic with respect to stochastic behaviors. Ooh, I still have trouble wrapping my mind around this. Okay, I find it to be weird. Okay, but I'm a physicist, astronomer, right? I'm used to things that actually depend on mass or pressure or density or abundance. I'm used to things that actually are physically dependent. It's dependent on past values and past changes. It's weird. But I accept it. It's a piece of math. I don't mind. Okay? Hey, by the way, if you simply combine them, xt is equal to this plus one of the w's. It's called ARMA. This one's has order p. This one is order q. It's called ARMA PQ. You just add the two together. Okay. So there's many extensions to ARMA type models. There's R and MA and ARMA. There's VAR when you have multivariate data. Evenly spaced identical times. Vector autoregressive, V is vector. You have ARIMA. And ARIMA has a differencing operator in it, and that deals with not all kinds of arbitrary non-stationarity, but it deals with a whole lot of non-stationarity, even periodicities. All sorts of changes in the mean value are modeled away by, it's not, as far as I can see, a coefficient. It's a operator. It's an operation. It's the differencing operator. It means x sub t is replaced by the difference between x sub t and x sub t minus 1. So you only consider how much did I change? How big was my step? And you just subtract it away. And it gets rid of the basic motion across the room. It's amazing. So I'm a little confused personally why AR and MA are regressions and the I is an operation, not a regression. But what can I say? At least I know how to do it. X sub t is equal to x sub t prime, the new value, is equal to x sub t old minus x sub t minus 1. Okay, I can do it. I can do it operationally. Removes all sorts of non-stationarity. Then I do ARMA on what's left. Hey, it's cool. I do it simultaneously. Fine, great, I don't mind. ARIMA. Do you know how many how many Google hits the word ARIMA has in Google? I did it last week. 1.5 million hits. ARIMA is really, really popular. Unless it means something in some language, like Japanese or Chinese or something. Okay, ARIMA is really, really, really popular. Does it mean anything in Korean? No.
We call it ARIMA.
Yeah, you're this, right. The reason is that ARIMA accounts for the sound of the wind in the trees. ARIMA, you can model the sound of the bubbling of a brook. The splashing of a waterfall. A Mozart symphony, which is non-stationary as far as I can see, but maybe the eye takes care. It gets loud and soft and stuff. But apparently, autoregressive models work for music. And above all, it works for human voices, human speech. I think I'm saying content-rich things in English. But ARIMA thinks I'm just doing some autoregressive process. And there's voice recognition is done. So your voice and yours and yours and yours and mine are different. And ARIMA has different coefficients. And apparently it's fairly consistent. There's the Feigelson coefficients that I can't believe it. ARIMA works over and over again. And it works for economists. Many of the behaviors in the economy are autoregressive and ARIMA works, except the stock market. The stock market ends up to have some nonlinearities. Particularly, you hear the news, well, it's middle of summertime and the stockbrokers are all on vacation and the stock market was very quiet. Or, there's a war somewhere and certain companies are going bankrupt and the stock market is going up and down every minute. It's called volatility. So the volatility is actually a hierarchical parametric model that looks like ARMA and ARMA, but it has the epsilon is itself autoregressively related. It has its own coefficients with respect to time. It could even be nonlinear. It could be sigma 1 t plus sigma 2 t squared. And that's epsilon, and epsilon is the stochastic indicator. So you get this sort of the envelope of the variations is autoregressive in addition to the values, in addition to the local small behaviors. And then there's our FEMA, also called FERIMA. Autoregressive fractionally integrated moving average. Fractional. I gotta read these books and figure out what they mean by fractional integration. I mean, I look at the math, I can see it, but I don't really understand it in my gut. But it ends up that this is the autoregressive way of talking about alpha. 1 over alpha red noise. The coefficient that comes out of our FEMA, PDQ, the D in the middle, which is usually an integer like 1 or 2 for ARMA. The D is 1.05 for our FEMA. That 1.05 is related to alpha. It's a nonlinear behavior that gives a certain form of parametric form of long memory autocorrelation, our FEMA. So by the way, in the first part of the homework, I'm telling you about gx5 minus 1. And all of a sudden, I have a sentence on the second page in bold. Students are requested to apply an FEMA model from a certain package. And the reason is I'm a little embarrassed. I'm not embarrassed. I'm entrepreneurial here. Okay. I didn't know about this package when I wrote the first edition of the book. I'm going to put it into the second edition of the book, but I haven't done it yet. So I want you to do it. I'm going to copy what you do. I'm going to learn from several of you, okay, of how does forecast FEMA perform for this particular data set. My personal guess, it's going to go from 27 coefficients to like 5 or something. It's going to be really, really compacted, I think. A very low dimensional system. That's my guess. But I don't know. So you're going to do my exploration for me, okay? Those of you who are going to do the homeworks. And in February, I'm going to look at it. I'm going to say, oh, that's cool. That's going right in my book. Okay. So I hope you don't mind. I crib off of you. Okay. But it's also exciting because you'll see that a 27 coefficient model is not a very, it's not a very parsimonious parametric model. That's because I chose the wrong family. I had an ARMA model when I had long memory. The ARMA model had a lot of trouble. I had to go out to 27. You see, to get those two guys, those guys, I had to put 27 coefficients in. It's just not right. So what it's going to do with our FEMA is that it's going to put in sort of a power law envelope to this, and that's just going to be 1 coefficient. And then it'll have a few more here for the ARMAs and 1 differencing operator, which isn't, the differencing operator isn't needed for this particular case because it actually has no trend. So in this case, the I isn't needed, but the F is in our FEMA. But they're all different. Everyone's different. So that's just what I think. So, I'm sorry. The one with the volatility is called ARCH or GARCH, Generalized Autoregressive Conditional Heteroscedastic Models. They're very, very popular among economists. They're all GARCHing all the time. Okay. So they've been doing ARMA so long, they don't even bother with ARMA and ARMA. They're all the way into GARCH. Okay. But GARCH is a nonlinear extension to ARMA. And I found a website that lists about 50 others. They're not 50 models, they're 50 model families Oh, some of them are nonlinear in this way or nonlinear there. Some of them are hierarchical. Some of them are there. It's just amazing how economists have just gone crazy for decades with autoregressive modeling. It's just amazing. So you too could be amazed by that. I mean, or just like, can't believe it. Okay, so here it is. I took the GX data. I ran AR on it with maximum likelihood estimation. And in this case, I got, it shows 8 coefficients. How did it know to stop at 8, order 8? That was because it ran the Akaike information criterion. And for reasons that I haven't quite understood, that whereas other modeling fields use the Bayesian information criterion, the time series people use the Akaike information criterion. They're closely related, but they're not exactly the same. And I don't know why. But it's well respected and it's no real problem. This one, this function is in R, base R. There's another one, ARMA is in base R. In this case, I actually told it what order. I said 622, and there it is. It gave me 6 ARs, 2 MAs, and two differencing operations. And there's my likelihood, there's my Akaike coefficient, there's my standard error on the coefficients. So most of these are significant. And there's my variance that's left. And here was my original scatter. Oh, no, I got it. Excuse me. My original scatter, as you remember, it was started around 70, and it was roughly plus or minus, let's say plus or minus 20 for most of them. So I applied the model. Then I found out there's autoregression in it there. Then I applied that model and got these coefficients. Now I looked at the residuals. There it is. It's 0 is the mean now instead of 70. The residuals are all within plus or minus 2. I went from plus or minus 20 to plus or minus 2. Most of the variance is taken into account by the model. The scatter is reduced by a factor of 30. Here's the autocorrelation of the residuals. Most of them are invisible. Oh no, darn it, didn't work. That's because I used ARMA instead of Arfima. I'm sure of it. So I want you guys to do this and get a really nice fit from Arfima. I mean, I'm hoping you will, okay? If not, go to Garch. I mean, I don't know. And then there's the Lejeune box statistic and the box pure statistic, and there's a whole little debate over which one's appropriate under which conditions and stuff like this. But basically, these are actually p-values. They're not maybe absolutely perfectly well-founded and all, but we actually, this model failed the Lejeune box test, and the p-values were not low enough. I'm hoping that you'll get good Lejeune box test values when you do Arfima. Okay, so I mentioned state-space modeling with the common filter, but there's sort of more to it. It could also be viewed as sort of an EIV, an errors and variable problem, where what you're observing is not actually the things that are linearly related in the space itself. So in an engineering system, maybe you can measure the speed of some engine and the temperature, but really what's going on is something to do with the pistons inside that you can't observe. So you form a relationship between the, which one is observed? Y is observed as a function of time. X is not observed, but is interesting. This A is usually a matrix, but it's in principle it's just a vector or a matrix of the coefficients relating them. There's some normal errors. And instead of having what you observe being autocorrelated in time, it's what you don't observe. The underlying state of variables are autoregressive. In this case, it's just AR1 in this particular simple case, with another error term that has a different variance. So this one has the variance of this is 1 parameter, 2 parameters. The variance of this is 3. This one might have, I don't know, 4 or 5 or 6 parameters. It could be anything. And so that becomes a parametric model. And it could be viewed, I think we would call it today, a hierarchical model. You know, this one, and then there's a hierarchy of this one's underneath. And that's typical of EIV models, errors and variable models. It could be that these two are related through known measurement errors, and that can be in which case this would not be a stochastic variable, but just known parameters. It doesn't have to look this simple. It could be nasty. What I like about state space models is that you can say y of t, the observed time series, is a function of, oh, I don't know, how about a periodic orbit? And for a star, a binary star, or a planet, I think it's about 6 nonlinear parameters, you know? The semi-major axis, and the period, and the ellipticity, and the inclination, and another inclination. It's like half a dozen of these parameters. So I can imagine there being half a dozen nonlinear parameters, and then plus, and this is what I like about state space modeling, is that then you can say plus a few autoregressive coefficients. Well, put in a Riemann, who knows? Plus, I don't know, a Gaussian noise with a couple of variances or something. You can sort of patch together complicated functions and that representing complicated physical systems and just run an MLE on it. You don't even need to call it a state space model. Just call it a likelihood. I don't know if it's a likelihood. It's a model. And then you use maximum likelihood to optimize it. And you use Bayesian inference if you have prior knowledge, prior constraints on the coefficients. If you know that this one cannot be less than 0.3 or something, then you have a constraint on it. And that weights the likelihood. It becomes a Bayesian calculation. Kalman filtering might be used if you want to do it once and then update it, or not necessarily. And there's a whole lot of things that are related to this kind of formulation. It can deal with non-stationarity. There's something called hidden Markov chains. I don't know much about it. You can run MCMCs on it, but you don't have to just maximize it. You can investigate all sorts of things. In parts of astronomy, we don't have real valued observations. We have integer valued observations, like in X-ray astronomy. We actually count the photons. So we actually have Poisson statistics, which immediately makes it a Poisson regression, which is nonlinear. And these are not Gaussian errors, but Poisson errors. And so there's a whole world of sophisticated parametric modeling that's available to the astronomers that we're not doing. No astronomer has done this, hardly. Okay. 6 o'clock. We're here till 7. Time for a break, because we're going into frequency space, frequency domain, and I need a break. We're going to move now from time domain to frequency domain. And here's some of the mathematics underlying Fourier analysis. The critical point is that we're starting with the time series x as a function of time, evenly spaced. Time is now just a stamp, an integer stamp. But we want to convert it to a function of frequency, which here is a small omega. And it's done through either this exponential that has an imaginary component, or it could be viewed as a regression with respect to sine and cosine, again with an imaginary component. These are complex. If one takes this discrete Fourier transform and squares it, the absolute value of it is squared, then that becomes what is known as the spectral power. Also, a plot of the spectral power against frequency is called a periodogram. And this classical periodogram was written down by Schuster around 1903 or something like that. And so this has been used for over a century. Note there also is a definitive relationship between the spectral density and the autocorrelation function that we just looked at. If you have the autocorrelation function with an infinite number of coefficients, then it has the same information as the Fourier transform. And you can go from the data to the Fourier transform and back again, providing you keep an infinite number of Fourier coefficients or frequencies. So these are transforms. you're taking your original data set, x of t, and transforming it into a different function as a function of frequency, or here a different function, a function of lags. If you keep all the coefficients, you can just transfer back. By the way, the wavelet is the same sort of thing. If you keep an infinite number of wavelet coefficients, then you have the same information as the original time series. So why do you do this? Because some temporal behaviors, and instead of having an infinite number of coefficients, have only a handful, a very small number, low dimensionality, of that's where all the variance is concentrated, or all the non-Gaussian variance, all the structure is concentrated. So it could be that the original time series is the most compact way of showing something. It could be the autocorrelation function is the most compact way of showing something. It could be, for periodic phenomena, the signal is concentrated in a very, very narrow, very few coefficients in the Fourier spectrum. And for a wavelet, it could be at a certain time something happened and it's concentrated in wavelet, some narrow part of wavelet space as well. So all of these transforms are available to the scientist. And in principle, you do them all. And you see whether or not which ones are most parsimonious and compact. And actually, one of the tricks is, if you transform it into one space, and you say, oh, well, there's only 10 coefficients that look really important, the others look like noise. If you set them actually to 0 and you go backwards, you've changed your data. But you often can denoise, get rid of even the Gaussian noise in your original spectrum, really rather nicely. In Fourier space, it tends to cause ringing, and these Wiener filters and these low-pass and high-pass filters that put zeros in portions of the Fourier space. So they're not widely used these days, although traditionally in engineering they were important. The one that's most used these days is wavelet denoising. It just happens to work really well in a lot of situations. So one of the only time I did a denoising exercise in this was the very last portion of the very last data set. I have a wavelet denoiser, and it worked great. It just came out, oh, beautiful, amazing. Kept the structure, got rid of the Gaussian, the small scale noise. Okay, I'm sorry, I'm just weak at math. I actually don't do the math very well for Fourier analysis. I guess I'm not good at complex analysis. I never did well in that class in college or something. So I'm actually, if you're an electrical engineering student, you spend a whole semester plowing through a whole textbook of this kind of stuff. It's really like a lot of math of a very particular type. It's also taught in math departments, this kind of mathematics. But I'm not too good at it, so I'm going to ignore this, okay? So, Fourier analysis reveals nothing about how the object, how the time series, the temporal changes with time. It reveals how the variance is at different frequencies. It assumes stationarity, that the beginning and the middle and the end of the time series have the same behavior. It just puts them all in the same bucket and asks, for this frequency, what's your signal? For this long frequency, for this very, very high frequency. For every frequency, it asks, what's the power in the signal? And if you have a periodic phenomenon, the planet's going around the star at 3.93 days, then you get sort of not much variance. And then all of a sudden you get to 3.93 and the power goes zooming up and you get a very strong spectral peak in your spectral power in your periodogram. And then it goes back to noise. That's cool. So Fourier analysis is great for sinusoidal periodic phenomena, strictly periodic phenomena. That's what it does well. It can be proved that the classical periodogram, the Schuster periodogram, is an estimator of the spectral density, the true spectral density, which is the Fourier transform of the autocorrelation function. But it ends up that it is actually not a consistent estimator. It actually has some mathematical problems, statistical problems, but I'm not too familiar with why that's true. Also, The proofs have really restrictive assumptions. The proofs is that you have an infinite data set, x of t is infinitely long. It is equally spaced and has no gaps. It is homoscedastic, every point contributes equally, and it is Gaussian noise. With purely periodic signals, no quasi-periodic, no jiggling the phases, no nothing, done changing the periods. And the shape of the signal has to be sinusoidal. And only under those very restrictive conditions do the theorems hold. And the theorems have asymptotic normality, and then you can get probabilities out of your spectral power. And here it is. The probability of getting a peak in the spectral power goes up exponentially. So if you get twice as high a peak, it's e to the 2 times more significant than a lower peak. So unfortunately, some astronomers read this in a 1988 paper in the Astronomical Journal that the Lomskargel has a Lomskargel periodogram, which is a generalized Fourier periodogram, has a probability that looks like this, and they used it for getting confidence intervals on the periodograms, in this case Lomskargel, but it's sort of like a Fourier periodogram. But they didn't realize all the assumptions underlying that. And these assumptions are so restrictive, like infinite data, that they almost never hold in astronomical data. Therefore, you cannot get analytical estimates based on asymptotic theory reliably for any Fourier-like periodogram. It's just unreliable. Well, maybe it's good in your case, but it's unreliable in general. So there are, every year, dozens of papers that put these nice little false alarm probabilities of 99.9 percentile based on this formula, and they're all unreliable. In fact, the issue of trying to get these probabilities is so important to the astronomers that there have been roughly 6, 8, 10 papers, methodology papers, in the astronomical literature just on trying to reliably get probabilities on Lomskargel periodograms. And those papers have never been evaluated by a real statistician. Anybody here good at Fourier analysis? I'm not joking. We really need someone to read them. Oh, they're just endless. They're huge and difficult, and only one of the authors has a PhD in statistics of those papers. His name is Chris Cohen, K-O-E-N, in South Africa. And he wrote a cute little paper, like a 3-page paper, in 1990, which is a long time ago, that everyone's forgotten. Nobody realizes how important it is. To see that if you use this kind of formula here to get the probabilities in a spectral spectral power diagram, you can be off by 4 orders of magnitude if just due to the one assumption that you, maybe I should have written that here, that you know that instead of knowing a priori the exact variance of the Gaussian noise, you had to estimate it from the time series. And the difference between an estimated sigma and a known sigma, as you may know from other branches of statistics, can change the theory of the math a lot, the mathematical statistics. And he showed examples where it was off by orders of magnitude in this case, using real data or simulated data. Okay, so here we are. Here's the same data set. I'm sorry I gave it again. Here it is, the fast Fourier transform. This is a manual one. This is where I actually did it using FFT, and I scaled it. And I got this from a textbook in time series analysis, how to do the scaling that makes it look right. But here it is. The FFT reveals at low frequency a broad sort of signal. And then it goes down to a rather very, very non-Gaussian noise, spiky noise thing. And then there's sort of a broad hump here around 0.4 in frequency. And then it goes down to non-Gaussian noise again. And that is it, ladies and gentlemen. That is the Fourier transform, or the square of the Fourier transform. The spectral power for gx5 minus 1. So in addition to the autocorrelation function showing significant structure, the Fourier transform also shows it. And it tells you different things. It tells you there's a quasi-periodicity over here and red noise over here. And we saw that in the autocorrelation function. This is the envelope that goes out to 30 lags. That's this. This is that up and down and up and down. We saw in the partial autocorrelation function quite clearly. And here it is again. Okay. So I think I already mentioned this, so I'm going to go fairly quickly. The Schuster periodogram is not a good estimator. It's formally inconsistent because the number of parameters grows with the number of data, which is not supposed to happen in a good regression problem. The discrete Fourier transform and probabilities depend on very strong assumptions I just mentioned that have to be strictly, there's something called strict stationarity and there's looser, but apparently this is the worst statement of stationarity, the most restrictive of them. And this is always violated, okay, by astronomers. So basically, we can do Fourier transforms. There's nothing wrong with doing Fourier analysis. It finds sinusoidal signals very nicely, but you cannot do statistical inference from it without a great deal of effort, and even then it tends to be tentative. Okay? So how can you improve this? Well, this is from every textbook in time series analysis. One thing to do is to take the spectral density and smooth it. I'm not saying smooth the data now. That was a few slides ago. We're smoothing the Fourier transform. And I usually smooth it using just a uniform filter, a box. I call it the Daniell kernel, a boxcar. That's the most common, but you don't have to use it that way. You can do a Gaussian filter, a Gaussian kernel, or some other kernel. So smoothing it instantly helps get rid of the spikes or reduce the spikes and gives you more ability to see things of interest in it. The other one is tapering. Now this one has to do with the non-infinite length of your data set. If you have a really long data set, tapering doesn't do much. And in fact, I think the one I have here, tapering didn't do much. It was mostly smoothing that helped. But if you have a short data set, particularly short with respect to the period of interest, let's say you only have 10 periods in your duration that you have available to you, then if you don't, if you do a Fourier transform, it tends to, it's like, I'm not very good at Fourier analysis, but for me, I have an analogy. If you're at the ocean and you have waves and you put a wall there, it tends to reflect off the wall. And then you get sort of beating and reflections with respect to the incoming and the outgoing. And the edge of the data set is like a wall, and the Fourier transform is trying to do an infinite thing, and it hits the wall, and it goes back and forth, and you get all these aliases and something called spectral leakage. And by tapering, when you get near the wall, just decreasing the values of your original time series, it reduces a lot of these problems with respect to that are caused by the finite length of the data set. So a typical one is that you might go some distance out. The critical thing is to guess what this coefficient is here. Do you take half the data and taper it, or 10% of the data, or 1% of the data? No one really knows, and no one knows whether should you use a cosine taper, or should you use a Parzin taper, or a Feigelson taper, or as now recommended, since you don't really know what taper to use, do multi-tapering and sort of use some sort of an optimization procedure that combines results from a variety of tapers. And that's what's recommended since roughly the 1990s. Okay, so this decreases bias, but it increases variance. Right? I'm sorry, something went off the bottom there. It probably says decreases variance. This is very much like in other smoothing situations. You have a bias variance trade-off. There we go. So this process of smoothing reduces variance but introduces bias. Tapering reduces bias but increases variance. So that's sort of good. It sort of means that maybe you can find a sweet spot where just the right amount of smoothing and just the right clever multi-tapering really gave me my best possible Fourier transform. So that's what they do in engineering schools. They teach you how to do this. Harmonic analysis, okay? And it's very much of an art, okay? And they magically teach you little strategies and stuff like this. No astronomer is doing this, okay? Astronomers are publishing this all the time. They think it's pure, that's it. They should stop. But the engineer says, no, look at all that crappy noise there. Okay, you can do better. You can do better, they would say. Okay, so here it is. I did it in R. I ran a program called Spectrum, a p-gram, a periodogram. I did a 30% taper. I did a fast FFT. I detrended, which wasn't important in this case. I did not take a log. And I used a modified Daniell kernel with 7 elements, a boxcar with 7 width. So I just did that. How did I choose 0.3 and 0.7 and 7? I played around a bit to look nice. And that's what I got. But you can see it definitely has higher signal to noise than the original one, right? That one. That one. It's just better. So astronomers should be doing this. Since you can't get probabilities anyways, you messed it up. You still can't get probabilities. So don't worry about it. Don't do probabilities. There's no statistics here. You're just exploring, essentially, in frequency space, what's going on. Okay, how else you can taper and smooth? You can also pre-whiten. Now, pre-whitening means that there really is a strong period. If you have a really strong period, it can sort of mask out lots of other weaker signals. So you might just take it out once you know, oh, at 3.94 days, there's a very strong amplitude sinusoid. You just take out that sinusoid from your data and do it again. And it's gone, okay? It's a filtering of strong signals. In astronomy, this is actually known as the clean algorithm, and is actually used for spectral imaging in the Fourier plane. And this is a paper that's not widely recognized, which is a clever use of the astronomer's ways of cleaning images, Fourier images, to Fourier time series. I think it's nice. I don't think it's brand new. I think it's just the astronomer's way of pre-whitening, and the engineers have their own way of doing it. And then I sort of mentioned earlier that you can filter it. You can filter it in the time domain, or you can filter it in the frequency domain. Okay, so you can in the time domain, if you fit a spline or an Orff-Email model, that's equivalent to a high-pass filter. It gets rid of the long-term trends, and it would reduce down the red noise. If you did a small kernel filter, it's like a moving average or a small Gaussian kernel. It would reduce the high-frequency noise. It's equivalent to a low-pass filter. So you can filter in the time domain plane or filter in the Fourier plane. They're not exactly the same, and there may be some advantage for doing one or the other in your case. Okay? You can run and find an autoregressive model. Maybe it's not even perfect, but use it as a smoother to just get rid of some signal in order to look for fainter things, or remaining behavior after you've said, oh, what's remaining after I take out a period that's very strong, or what's remaining after I take out some, let's say, long-term trends. You may not be interested in that, but these are ways of getting higher dynamic range out of a spectral density. Okay. Now, the unevenly spaced data that astronomers have is a big problem. So it ends up that if you view the problem not in terms of complex, frequencies and complex numbers and infinite sums, but if you view it as a regression problem, a least squares regression problem, you can do least squares regression on sines and cosines for each frequency. And the least squares approach leads to this solution here. So the least squares approach was started in the 1960s and 70s elsewhere. I don't know if it was engineers or mathematicians did it. But it was picked up by Lohm, who was more or less an unknown physicist, and Scargill, who became astronomy's most distinguished time series analyst. And Jeff, who is an old friend of mine, and Jogesh. Jeff, is Jeff Scargill coming to SAMC this time? I don't think so. I haven't seen his name. It's too bad. He's really very wise and very good. A nice man. He says he's really surprised. He wrote this paper. He wrote like a series of 10 papers on various time series things. And number 3 paper in 1982, he just wrote this paper and he put in this periodogram. It was a variation of the least squares approach. And now has 2,000 citations. Okay, this is like the most important astrostatistical tool we have in time series analysis. This is the Lohm-Scargill periodogram. So the trick is this tau. If tau is 0, this becomes just a Fourier transform. But tau, which has this, tau is the solution to this nonlinear equation. So this is your time series, this is your time series, this is for a given frequency. So this can be computed. Then you take the arctangent of this, and then you find out what tau is. You put tau in this one, and then do this weird sum, and that becomes the Lohm-Scargill periodogram. I have no idea why the math works. Don't ask me the math. Okay. A guy named Larry Bretthorst, who's a brilliant, trained as a physicist, became a biostatistician, but really an applied mathematician, in my opinion. He made remarkable innovations in short duration Fourier spectroscopy, Fourier transforms. And he got a solution that got rid of all of the aliases. They were very remarkable. He transformed nuclear magnetic resonance machines just in software. They became far more sensitive because of his work years ago. And he came to one of our meetings and met Scargill and heard about this, and he knew a lot about this kind of stuff. And he wrote a paper in one of Jogesh and my conference proceedings that that gave some sort of foundation to Lohm-Scargill. It's an MLE. It's also a Bayesian inferential solution for a reasonable prior, and there's generalized Lohm-Scargill that solve broader classes of problems. So Fourier transforms are over there, very simple, and Lohm-Scargills are here, and then there's other problems, other situations. And so there's a whole sort of environment in which Lohm-Scargill periodograms live. I like that. I mean, I'm not a good mathematician. I can't really talk to you about it. But the fact that it's a solution to Bayes' theorem with reasonable priors, the fact that it's a subclass of broader generalizations is great, in my opinion. So I think it has a certain, convincingness about it. Jogesh has a critique that he'll have to explain to you if you really want to know. But it's a certain assumption in the appendix of Scargill 82, which he says is not wrong. The assumption's needed to do the theorem, to do this. The problem is that assumption is not satisfied by most astronomical data. Some sort of independence of something or another. I'm not quite sure what. And so Jogesh thinks it might be a biased statistic, and some physicists think at high frequency it's biased, but most astronomers don't care about that. And it's used mostly to find peaks, to find a periodicity. But so it probably has a lot of virtues, but it may have some problems too. It's very hard to get probabilities out of it in practice. Now, what most statisticians don't know, and what I would, there are statisticians in the room right now, I want you to wake up and listen. Because in 1972, in 1983, astronomers who are just astronomers invented new periodograms that have never been evaluated by statisticians. And they're not mathematically difficult. They're very, very simple. And so they are non-Fourier periodograms. Periodogram means it's a statistic, a signal, as a function of frequency. That goes up, or actually one of them goes down, when there is a periodic signal there. And why did the astronomers invent something when Fourier already had stuff for 200 years? Because it deals with unevenly spaced data, and it deals with heteroscedastically weighted data, measurement errors. And you might say, oh, I don't know, Fourier transform can't do that. That's because they didn't use any transform. They did it all in the time domain. They made a frequency periodogram, but they calculated it in the time domain. By the way, this formulation is in the time domain too. It gives you a periodogram as a function of frequency, but the calculation is a bunch of sums in time. So there's nothing wrong with that. So what do? Let's take Stellingwerf's phase dispersion measure, which has another 1,000 or 2,000 citations. It's been extremely popular, particularly in the 1970s, 80s, and 90s in something called variable star optical astronomy. But it's still used today in other fields, still widely used. So what you have is you have this time series, but it's irregularly spaced. Blub, 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 blub. Blub, 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 blub. That's your data. Really lousy data. And each one has a different measurement error, a different weight on it. So what you do is you take a frequency, you take a period, let's call it a period, and you fold it, the data modulo that period. You use the modulo operation. So let's say the period is 10 periods in the duration. So you do one period, you take the data, and then the next point, it starts at 0 phase, and and then there's another 0 phase another 0 phase. So the time series gets recollected in a diagram that runs from 0 to 0.5 to 1 in phase. Maybe I'll draw it here. Some sort of intensity versus time. It becomes intensity as a function of 0, 0.5 to 1. The data are distributed in the same intensity, same data, same values are distributed in phase. This is called phase. Phi for phase. This is time. And this is modulo a given period, p0. And you do it for 1,000,000 periods. So it just redistributes the points. Well, why is this of interest? What Stellingwerf does is he divides this arbitrarily into bins, maybe 10 bins. And he just calculates the weighted mean and the weighted variance. And if these things are randomly distributed, he looks at the between variance, the variance of the means between the bins, and compares it with the variance within the bins. And if they're roughly the same, then that was a rather ordinary random situation. But for a particular frequency, all the high values might collect up here. And then the mean is big, but the variance is small there. And the between variance goes zooming up, while the within variance doesn't change much. And you get a periodogram of Stellingwerf's statistic all of a sudden has a big peak. Actually, I think his gets a little dip, a big dip, not a peak, at a particular period, p0, where there is a signal. Now this has another advantage. We have signals that are not sinusoidal. We have signals that look like that. Boo, boo. Actually, they're usually upside down. Boo, 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 boo. Periodic, but not sinusoidal. Sinusoidal would be boo, like that. We even have weird ones, elliptical orbits. Ooh, non-sinusoidal shapes that are neither box-like nor sinusoidal, like they're sort of weird. We have all of the above and probably more. So this deals with non-sinusoidal shapes and deals with heteroscedastic weighting, because you can, when you do this weighted mean, you can take account of the measurement uncertainties. And Stellingwerf, and we sum them up using something called chi-squared. It's the sum of the squared differences that are weighted by the measurement errors. And everyone loved it in astronomy. Everyone still loves it in astronomy. Thousands of times it's been loved. No statistician has ever looked at it. I'd love to see, for example, a bias versus variance measure criterion for estimating the number of bins. I'd like to get rid of the bins and do it as a kernel density estimator with some sort of optimized bandwidth. There's all sorts of great stuff. I suspect it's a grad student level problem. I don't think it's going to be hard. But I really want someone to write a lovely paper this semester on the statistics of Stellingworth's method and how to improve it using standard methods. You know, open up Wasserman's little book, Nonparametric Statistics. You should be able to do it. Anybody interested? Don't answer, okay? If you're not interested, talk about it in the hallways, okay? At UNC and at SAMC, okay? It should be very simple for you guys. You just don't even know that this is out there. But this has been used so many times that it's worthwhile somebody getting some asymptotic theory and some improved methodology out of it. It's not very hard. Drewetsky's been only used a couple hundred citations, and what he did is he realized that it's not always good to bin things. So in the same data set, he did as follows. He starts at the beginning, he ignores the measurement errors. He draws the lines connecting the sequential points. This is all modulo the period. And when they go up, it goes up there. And when it goes down here. And he then says, how long is that string? Called a minimum string length measure. Because when they all line up, then all the top ones are there and the string length is smaller than in the typical one where it's constantly go up, down, up, down, up, down, up, down, up, down. It's constantly going up and down and the string length is longer. It looks for the period that has the minimum string length. I think that's cool. So I found somewhere the Durbin-Watson roughness statistic, which is very similar, except that one is vertical distance from the mean, the sum of the vertical strings. This one's slightly tilted strings. And the tilts are different because these are unevenly spaced. So it's actually not exactly the Durbin roughness statistic. But it's sort of, it shouldn't be very hard for you guys to think about that one. It's non-parametric statistics, it can't be that hard, okay? So Dvoretsky is more elegant in my opinion because it's unbinned, but for reasons that I don't understand, it gets only 10% of the usage of the other one, and people say it's not very sensitive. I don't know why they say that. It's an interesting question to me. To me, it's simpler and more elegant, and yet it doesn't work as well. Damn it. Okay? So that's sort of interesting. So I really think that Stellingworth and Dvoretsky is worth thinking about. These are periodograms that are designed by astronomers for astronomical data. They work well. No statistician has looked at them, unless it has another name in your field that I just nobody's found. But I suspect it's relatively easy to work on. Grad student level problem, that's my guess. I don't know. In non-parametric statistics. The fact that it makes a periodogram is not the point. Because for each period, it's an independent calculation. So it's really a calculation done here in this space. And then this is just a plot of 1,000,000 values of those. Then it becomes, maybe the hypothesis testing then becomes a multiple hypothesis problem. Now that might be interesting. Maybe that's a false discovery rate problem or something. That's to get probabilities. I don't think anyone has claimed they have probabilities out of Stellingworth's PDM. I don't know. I've never seen one. So I don't think people even assume they can do it. That's cool. So there we go. I think that's really quite interesting. That's my opinion as an astrostatistician from the astro side. I'd like to interest astrostatisticians from the stat side, because I don't think it's going to be very hard for mathematical statisticians to think about it. We have some data in X-ray and gamma ray astronomy where it's Poisson data. These are really event sequences We do not read papers in sequential analysis, which are designed for sequences of events, time series of events. There's a whole series of books by there. Wolds and others wrote theorems on this many decades ago. Lord Rayleigh wrote a statistic for this. We use that. So this paper rediscovered Lord Rayleigh's statistic and wrote there's a generalization of it written by some gamma ray astronomers called the ZN squared test. It's a test for periodicity in Poisson distributed photon arrival times, and for very, very high rates, it becomes the Fourier transform. So it's a Fourier-like calculation with Poisson data. My personal opinion is that there's a little less activity using this than up here. More people are interested in this than this, just because this is Gaussian data, this is Poisson data. But this is also interesting. Lord Rayleigh was a physicist, but he was a brilliant mathematician. But that was over 100 years ago. So I could imagine someone today looking at the Rayleigh test, and I forgot the name of this test. There's a generalization of it. And taking a look at it from a mathematical statistical point of view and seeing if you like it. And can you learn anything about it? And maybe you could work for a week, learn something about it, and publish a paper. In the astronomy literature, or your own literature, I don't care, that maybe does some asymptotic theory or something, or talks about bias, or some sort of optimization. I'm not sure. Now, two people who you may know. You may know Tom Loreto because he's closely related to Samsey, and you may know Phil Gregory, who's a generation older. He and Jeff Scargill are sort of like the old timers. So Phil is retired, and Jeff is sort of thinking about retiring. But Phil Gregory is a wonderful guy, and he wrote a wonderful book in 2005 on Bayesian inference for physical science, the first such book written. And they got together years ago and wrote down this Bayesian approach to the following problem. It's sort of related to this. It is for each folded modular period, it divides it into bins, but it solves for these mean levels as parameters of the model. So it's a higher dimensional system, higher dimensional model, where it asks what possible weird shape could it be at this period, and let's choose the best shape such that it optimizes some statistics such as the Sellingworth statistic or some other statistic. And they happen to write it down for Poisson events, but I believe it can be done for Gaussian data as well. This is not widely used. It's sort of too narrow. Non-sinusoidal Poisson data is not that a common situation. But it's elegant, in my opinion. The paper is elegant, and I think also should be looked at again. And since Tom Loreto hangs around here, you could look at it with Tom Loreto. and it could be Tom would say there's nothing to be done, it's great, or he doesn't like it, or he does like it, I don't know. But in my opinion, it's another approach, it's another variant approach to periodicity searching with lousy data, with unevenly spaced data, with non-sinusoidal shapes, and with heteroscedastic weighting, or with Poisson events. So my conclusions for spectral analysis, Fourier analysis, harmonic analysis, I can't tell the difference, they're all the same to me. Unless you have something totally trivial, a great data set with a single strong peak and you just don't have any problems. Please, astronomers, smooth your power spectrum, multi-taper it, consider filtering, do pre-whitening and either and filtering either in the time domain plane, like taking away trends, or in the spectral plane, like high pass and low pass filters, and do Loam-Scargills. And I see no reason why you can't do all of the above at the same time. I don't see why you can't smooth a Loam-Scargill. It's just a generalized Fourier transform, power spectrum. Why not? I don't see why you can't taper it. Taper the data and then do a Lomscargel periodogram. It's got to help under certain situations, et cetera, et cetera. So I don't see people being flexible enough. They say, oh, here's the Lomscargel periodogram and publish, figure 3, you know. They just do it and then they stop. Whereas if they took a whole class in electrical engineering, they would learn all the artistic, amazing ways of doing things, you know. If you took a class in stat department, you'd learn Box-Jenkins and all the wonderful ways of doing ARMAs. And astronomers don't take these classes, so they don't do anything. They don't do enough in time series analysis. They don't analyze their data enough. And then they overinterpret what they see often, not often, but sometimes. Okay? So I think, but it's very hard to get significance, to do statistics on these in the Fourier plane and harmonic. It's very hard. Basically, don't do anything with an exponential function. It's just hopeless, in my opinion. If you really need to do it, and the planet people really need to do it, and the star people really need to sometimes, I'm sorry, I touched something. Do simulations. You can always permute your data and bootstrap your data, but permuting is probably more reasonable for time series. Keeping the observation times fixed and permuting the data. But I'm not saying you shouldn't do that, but you can't tell everything from that because you've gotten rid of aperiodic autocorrelations at the same time as you've gotten rid of periodicities. So yes, you can permute your data, and astronomers are doing that, but it's really not enough to convince yourself the peak is real. The problem is, in so many astronomy papers, is they see a peak in one of these, in a Stellingwerf or in a Lomscargel or in something, and they say, oh, I found a periodicity. But it's really an autocorrelated, and it's really an autoregressive system where they just didn't have enough data in duration. They didn't have enough data in irregular spacing. You take any autocorrelated phenomenon and do irregular spacing, you often will get a peak, a spurious peak, in some sort of harmonic power diagram. It's just meaningless, ladies and gentlemen. You take another chunk of data from the same thing, you just get another spurious peak. There are actually papers from the 80s and stuff where they would say, oh, I found a period for this star. Oh, I found a different period for the same star. I found a third. Eventually they'd probably conclude they're all wrong. Wrong. There are papers galore from the 70s and 80s that are wrong on period analysis because they had autocorrelated phenomena that were poorly spaced and they didn't understand the methodology, the meaning of it. And there's controversies today in exoplanets. The biggest one is, okay, I'll tell you an anecdote. Right. So, you know, starting in '95, we found these planets going around the stars, and usually it's from unevenly spaced data with these radial velocity curves and that are non-sinusoidal shape, and it's very hard to do the statistics, like I've been saying. So one of the groups that was a little less statistically sophisticated on a system that already was known to have 4 planets, GJ581, they claimed a 5th planet. The 5th planet happened to be exactly where Earth is. Warm, habitable planet. The first author of the paper, after it was accepted, I was not an editor, a statistical editor at the time. Okay, the statistics were weak. The first author named the planet after his wife. When it was accepted, held a press conference. It received 250,000 Google hits. It was on the front page of USA Today, the Washington Post. He said to the press, I'm 100% convinced there's life on my planet. It got all over the press. Today, Phil Gregory wrote a paper, The 5th Planet Doesn't Exist. more data was collected by the Geneva people. They couldn't find the planet. Some people can find the planet. We've got to remember, you have to pre-whiten it 4 times with 4 other planets. So you've completely changed all your numbers. You're looking for a 5th periodicity. It's very difficult. My own personal opinion is, I don't know. Maybe there's a 5th planet. Maybe there isn't. We should ask Eric Ford, who also visits here. What does he think about GL 581, 5th planet today? I think there may be enough data, and guys like him have a lot of expertise, so I'd be interested to hear what he wants to say. But it was a scandal that every newspaper in the world was announcing that there was life on a planet when it's not even clear the planet exists. And the entire issue is the statistics in Loam-Scargill periodograms and whether permutation tests are sufficient after 4 levels of pre-whitening. So I'm not talking about minor issues in astronomy. I'm talking about major scandals and major discoveries. We really care about the 5th planet. We really care about the small, weak planets with the really weak signals, because it's easy to find a Jupiter. It's really hard to find an Earth. They were so small. The effect on the brightness or the effect on the velocities is very small. So we really need these methods. That's why so much of the concentration at SAMC is on methodology for exoplanets. The reason why most people are not even talking about this, Loam-Scargill's Eric Ford, let's say, probably doesn't talk too much about this, is that he knows so much of the physical processes. He knows all about these ellipses, and it's all parametric, nonlinear parametric. He does a 30-dimensional nonlinear parametric model and has to run AIC, or Bayes factors probably, to try to decide, is it 30 parameters for 5 planets or 36 parameters for 6 planets? So he's doing high-dimensional Bayesian modeling as an alternative to sitting there and trying to guess your way through these periodograms. I'm not against it. I think Eric is probably doing the wise thing. He knows the physics. He should use his knowledge. He then has a very difficult statistical problem, and he tackles it very, very well. So there are other ways of doing it, but there's a lot of literature with Loam-Scargills out there. Some of them on planets, some of them on other things. A lot of the work is of really mediocre or unreliable analysis. Well, I don't really have much else to say. I have a couple of slides here on non-stationarity. It's really inadequate. I personally would now add slides on ARMA and ARMA, because the I is the differencing operator that does a really nice job on non-stationarity. But wavelets are really very, very good. I don't think astronomers are doing enough wavelets, in my guess. It's really nice. Wavelets are really cool. And I think we should be doing more of it. It's sort of like a 3D Fourier transform. It's not a Fourier transform, it's a wavelet transform. But there's another dimension. It's more like time frequency Fourier transforms. It's the scale of the wavelet, the location of the wavelet, and of course it gives the amplitude. It's not very appropriate for periodic. I mean, you can do it for periodic phenomenon, but it's designed for particularly non-stationary aperiodic phenomena like explosions or changes that occur. Jeff Scargill has a wonderful paper on a wavelet analysis of an X-ray source, sort of like GX 5-1. Beautiful work years ago. There are others too. Oops, sorry, that's repeat. Oh, repeat, what's going on? I just have all these extra slides. I'm so sorry. There's a method called Bayesian blocks. It's rather popular. It was developed by Jeff Scargill a decade later. He just wrote a recent paper on it as well. And actually, he doesn't mention it. But really what it is that it's a method of change point analysis. He should have said that. It's a likelihood-based, it's a parametric change point analysis. It's a parametric model. You know what the model is? The model is a sequence of constant values. That the values are constant here, then there's a change point. And then it goes up to a new value, then there's a change point. And it goes down and up and down like that. This one had 6 values. You have to solve simultaneously for the 6 mean values and the 5 change times. And you have to solve for the number 6 because you don't know ahead of time that there's 6. So he calls it Bayesian blocks. I'm not sure it's that Bayesian. I'm not sure what the priors are that are. It's basically a likelihood. It's segmented, piecewise constant model. By the way, I don't like the model because there's nothing in the sky that actually has this green behavior. Boom, 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 boom. Nothing goes like that in the sky, intrinsically. So it's actually, histograms are not very good for physical processes. So I don't like the model. Astrophysically, but I like it just operationally. It's really very useful, okay, because it actually tells you when to ignore changes and when to not ignore them. He does it for events. These are events, but I don't see why it can't also be done for grayscale, for real numbers. I'm not sure he does it. I think you change it from a Poisson to a Gaussian statistical process underneath the basic model of segmented, piecewise constant model. You write down the likelihood, you solve for 6, and you solve for the values. It's a great idea. Okay. It's used, I think there's a couple hundred citations. Not bad. It's being used. I've used it in my work. I'm an X-ray astronomer when I'm not doing statistics. Has not been evaluated by statisticians other than Jeff Scargill, who's a very good guy, okay, very knowledgeable statistician. But I think Tom Laredo had some complaint about it. I think Tom didn't. It's not that he didn't like the solution. I think there's an effort to get confidence intervals on it, and that's probably hard. We all know confidence intervals are harder than estimation in many regression problems. So it's a regression. I think it's a clever one and often very useful. So this page are references of statistics books. A couple of them are from the engineering, like Malay's book from A Wavelet Tour of Signal Processing. But Maurice Priestley was a professor of statistics at Manchester. Shumway and Stouffer. This textbook is taught certainly in engineering departments, but probably also in stat departments. Kingman was a statistician. I love this cute little book on Poisson processes. It's a little tiny book. Here's a book that no one's reading. Genshiro Kitagawa is essentially Japan's greatest living time series analyst. I think he certainly was director of their Institute of Mathematical Statistics. I don't know if he still is. He wrote this book that nobody reads that is full of astronomy and geology applications. It looks very, very much like our data in many cases. It's really cool. It's a Bayesian approach to time series. And since I've never met anyone who's ever read the book, I'd be interested in someone looking at the book and seeing from a 2016 perspective if it's interesting. I thought it was. This is the world's favorite introductory textbook. Chris Chatfield, The Analysis of Time Series and Introduction, 6th edition. It's a little tiny paperback, red paperback. Should be on everyone's desk who does these things. It's really cool. And then one of the famous books emphasizing Fourier analysis by statistician Brillinger from, I think, Berkeley, though I'm sure he's retired or dead. But my last slide, you don't know my last slide, because these are the references in the astronomy literature that basically are methodology articles on time series analysis. The only field of statistics where there is a consistent body of literature of pure methodology in the ASTRO literature is time series. And the reason is we have unevenly spaced, heteroscedastically weighted time series. So we have to develop it. So there's the reference for Stellingworth. APJ means Astrophysical Journal. There's the reference for Drawetsky. MNRAS. It's like JRSS. This is monthly notices of the Royal Astronomical Society. The journal's been around since the 1820s. Okay, so it has Gregory Laredo, App J. Okay, it's usually one of those two journals. The European journal is called Astronomy and Astrophysics, but they don't do much methodology. But they did do a least squares box fitting algorithm that is widely used for planet detection. And then there's this guy named Roberto Vio who left astronomy for industry years ago in Italy. And he still writes what I think are brilliant time series articles in astronomy literature, even though he has a job in some way, such as this one, Time Series Analysis, Limits and Potentialities. Good stuff, Roberto Vio. I never met him. I'd like to meet him. So that's it, ladies and gentlemen. 2 hours of all of time series analysis in 2 hours, meaning time domain and then frequency domain. That's what I mean by all of. Okay. So I hope you liked it. So I give this particular talk, this particular lecture, to groups of astronomy grad students around the world. And I always ask them, did you like this? And they always say yes. I can't believe it. They're like, this is the young ones. They're starved. They're like hungry for basic information. I said, why don't you just read Chatfield? You'd get it all, you know. Well, they don't know about Chatfield. They like, I don't mean to brag, they like to hear it from me, okay? Because I can talk about stars and give an example that's not from social science or something. And they just, but I'm not saying anything new here. I mean, a little bit. I just tilt it for astronomers. They really like it. So there's an incredible ignorance in the astronomical community of standard time series analysis. And they hone in on, Stellingworths and Lomscargill and a couple things they just always do. They just do it over and over and over and over again, which frankly, sometimes it works great. And sometimes it's completely unreliable or inappropriate. Some use wavelets, not bad. Some are doing excellent work. People associated with SAMSI tend not to be among the ignorant people doing lousy work. You don't see them here, okay? It's out there. So I do a lot of the basic education, trying to teach this level. But this is a research institute. So I'm glad you heard this. I think even there's some research challenges here, like evaluating these papers that have hundreds or even thousands of citations. And saying, if you guys can say something about it. You might want to get a professor of mathematical statistics who knows asymptotic theory or something on your side. I mean, I don't know if it's hard or it's easy, but I suspect it's not that hard to do. And I'm sitting there in room 174, and basically I'm a time series guy and I like this stuff, okay? So I know this stuff. If you want to come chat with me anytime, feel free. I'm here downstairs, not continuously, but most of the time from now till May. Most of the semester I'll be here. You have to do a project. A few of you are taking the class. Maybe there's some slide in this you say, I don't want to do a data set. I want to do a project based on something on the slide. Come to me. We'll do a project that you want to do. Okay? You don't have to do a project like I described. You need to do a project. Okay, I'm 3 minutes late. Bye-bye. I'll see you next week. Next week is all R. Please bring your computers. Not that you don't. But bring your laptops, and I will have an R script, and we will cut and paste and talk R next time.